Yes, so welcome once again to the class. After so many days, we are meeting once again, and I will try to upload regularly from now onwards. Actually, uh, I was facing some trouble as there was construction going on at the home, so that's why. So, in the previous lectures, if you haven't watched the previous lectures, then you can surely go to the link in the description given below this video, and also you can uh, press the I tab. Okay, so reference frames, as we have already learned what is third law of motion of Newton in the previous lecture, and so we are moving towards the reference frames now. Okay, so reference frames are of two types. Those are actually inertial frame and non-inertial frame. Now, what is meant by inertial frame and what is meant by non-inertial frame, we will look at it now. Okay, so inertial frames are those frames in which first law of motion holds. Okay, so as the first law of motion holds in the inertial frame, so the other two laws of motion will also hold good in it. Okay, if the first law of motion holds in inertial frames, then second and third law of motion will also hold in the inertial frame. Why? Because all the laws of motion of Newton are interconnected with each other. So as the first law of motion holds in inertial frame, so second and third law of motion will also hold in the inertial frame. This particular frame, which is inertial frame, it is either at rest or in uniform motion. What does it mean by being at rest? Being at rest means either it has zero velocity, okay, or either it is in uniform motion. What does it mean by uniform motion? Uniform motion means motion with a constant velocity along a straight line. Okay. Now, motion with a constant velocity along a straight line implies that there is no curved motion. Okay. Even if the speed remains constant, still the velocity changes. Okay. Suppose a frame is moving in a circular path. Suppose this is my frame of reference, and this particular frame of reference is moving in a circular path, suppose. Okay, so do you think it is uniform motion? Even if its velocity, suppose its velocity at any time is v, do you think it will be uniform motion? No, it will not be uniform motion, because even though its speed v is constant, still its velocity is changing, because velocity is direction dependent. Okay, velocity is a vector. So this particular frame which moves in along a curved path will not be an inertial frame. This particular frame which moves along a curved path, it will not be an inertial frame. Okay, so first law of motion holds in inertial frames. This implies that second and third law of motion will also hold. It is either at rest or it is in uniform motion. Okay, I also told you the meaning of uniform motion. In this particular frame, which is the inertial frame, if force is 0, then acceleration will be equal to 0. Okay, if no force acts on a body in this particular frame, which is either at rest or moving with a constant velocity. Okay, so in this particular frame, is if force acting on an object is 0, then the acceleration on that object will also be 0 only. Okay, now non-inertial frame. Non-inertial frames are those frames in which laws of motion do not hold. Now, if even if I say that first law of motion does not hold, then this will imply that the other two laws of motion will also not hold good, because non-inertial frames are such frames where uh, no law of motion actually holds. They are actually accelerated frames. Okay, they are what? Accelerated frames. Accelerated frames means either they are moving along a curved path. Okay, these frames are either moving along a curved path, or even if they are moving along a straight path, still they will have some acceleration. Okay, so if they are moving along a curved path with a constant speed, like a circular motion with constant speed, still they will be accelerated frame. Why? Because the direction of velocity is constantly changing, and if they are moving along a straight path, but not with a constant velocity. Okay, the velocity is changing every time. That is there is acceleration. Okay, acceleration is equal to rate of change of velocity. Okay, so if there is acceleration, then it will be non-inertial frame. In these frames, these non-inertial frames, acceleration is not zero even when force acting is zero. Okay, so if you keep something in an accelerated frame, suppose you are in a lift. Okay, in an escalator, that is lift, which we call lift in a general day-to-day life. And in that lift, if you keep a ball, so there is no force actually acting on the ball. Okay, but its acceleration is not zero because it is present in an accelerated frame, so it will have certain acceleration even if there is no force acting on that ball kept in that lift. Okay, so such is the situation. Or if you are there in a merry-go-round. Okay, merry-go-round uh, in a mela. Okay, merry-go-round in a mela, we can say, fair. Okay, merry-go-round in a fair. If you are there, then what happens? Suppose you keep a ball with you while you are sitting in the merry-go-round. Now what is this merry-go-round? Merry-go-round means this kind of a machine is there in which you sit. Okay, this kind of machine, it has an axle over here, it rotates. Okay, and if suppose you are sitting over here along with a ball in your hand. Okay, then do you think this ball has any force acting on it? Surely there is no force acting on this ball which is in your hand. But as this merry-go-round is rotating, so it is an accelerated frame. So this particular box cabin in which you are sitting, this is accelerated. So even if the force acting on that ball or your own body is zero, still you will have acceleration. Okay, there is no external agent which is applying force to you. Still, as you yourself are in an accelerated frame, so that's why your acceleration will not be equal to zero. Okay, so such is the situation. Remark: the earth is actually a non-inertial frame. Okay, but why is the earth a non-inertial frame? The reason is very simple, because earth is rotating on its own axis as well as revolving around the sun. Earth is rotating on its own axis as well as revolving around the sun. So that's why earth is actually a non-inertial frame. Okay, but for many practical purposes we treat the earth as an inertial frame because motion takes place with speeds which are not too large. Okay, the surface of the earth rotates with a very large speed. Okay, the surface of earth rotates with a very large speed. So if you consider that earth is a non-inertial frame, the problem will be very much complicated. Okay, whatever kinematics equations you apply and whatever Newton's laws you apply while you are standing on earth, if you try to include the calculations of non-inertial frame, suppose you are considering that the earth is rotating and revolving, so all those calculations if you include, you will find that the calculations give such results which do not deviate much from the inertial frame. Okay, the calculations give such results which do not deviate much from an inertial frame. So for practical purposes we take earth to be a non-inertial frame. Okay, inertial frame. So for practical purposes we take earth to be an inertial frame although it is non-inertial, because motion takes place with speeds which are not too large. If motion suppose takes place with speeds which are very large, then surely earth will be non-inertial frame. Okay, because when you will calculate eventually in the kinematics equation, in the Newton laws of motion and all those calculations, when you apply, when you take the rotational acceleration due to gravity of earth, the effect on acceleration due to gravity because of earth's rotation, when you include all these calculations, okay, you will eventually find that there is not much difference, okay. But for huge speeds which are comparable to the speed of rotation of earth, okay, for those huge speeds, actually you cannot take earth to be inertial. In those cases you will have to treat earth as a non-inertial frame, okay. But such situations will arise rarely in your questions, okay. So inertial and gravitational mass. The equation F equal to ma can be used to measure the mass of the body. F equal to ma equation can be used to measure the mass of the body. How? When you take the magnitude of force over here, when you take the magnitude of force over here and magnitude of acceleration over here, and you simply bring this to the left hand side, acceleration, magnitude of acceleration to the left hand side, then you can surely measure the mass of the body. Such a mass is called inertial mass, okay, because mass actually measures the inertia, and this is equation of inertial, okay, inertial law of motion, okay. So that's why this particular mass is called as inertial mass. Let the same force F act on two bodies of masses m1 and m2 so as to produce accelerations a1 and a2 respectively. So if the same force F acts on two bodies of masses m1 and m2, and they produce accelerations a1 and a2 respectively, then what will happen? F will be equal to m1 a1 equal to m2 a2. Never do this mistake, okay. Some students do the mistake that they write F vector equal to m a vector, okay. Then what do? They will write m equal to F vector divided by a vector. So this is a completely wrong concept. Why this is a wrong concept? Because the division of two vectors is never defined, and you have divided two vectors over here. So division of two vectors is never defined. That's why when you want to calculate the value of m, you will have to simply take the magnitude, okay. You will have to simply take the magnitude of F divided by magnitude of a. Only then you can find m with the help of this formula, okay. So keep this thing in mind, that division of two vectors is not defined. So F equal to m1 a1 equal to m2 a2, that's why m1 by m2 equal to a2 by a1, okay. M1 by m2, this will come over here, so it will go in the denominator. This is in the multiplication over here, so it will go in the denominator and will come in the division, that is in the denominator. So m1 by m2 equal to a2 by a1, this is your equation number 1. If m2 is known, suppose, then m1 can be calculated by measuring a2 by a1. The mass measured in this manner is known as your inertial mass, okay. So mass measured in this manner, where you will take this m2 to the RHS and measure m1, okay. So you are measuring the mass on the basis of a force applied on two different mass objects, okay. So mass measured in this manner is known as your inertial mass. Another way to measure the mass is by weighing it, okay. You can weigh it. Now how to weigh a mass? You can compare the gravitational force acting on it with that of a standard mass. So here F equal to ma becomes W equal to mg, okay. So when you are keeping any mass in the presence of Earth's gravitational force, so weight will be equal to mass into acceleration due to gravity, okay. The mass measured in this manner is known as the gravitational mass, okay. So mass which will be measured in this manner by taking modulus of W divided by modulus of G, okay. How will you measure mass over here? Mass will be equal to your modulus of W divided by modulus of G, right? So in this manner, if you measure the mass is known as gravitational mass, okay. experiments have established that inertial and gravitational masses are equal. Okay, experiments have actually shown that inertial and gravitational masses are equal within an error of a few parts in 10 to the power 10. So there is an error in a few parts in 10 to the power 10, but these two masses are near about equal. Okay, there is one experiment also related to this, okay, which we are not going to learn as it is not there in your syllabus. But one experiment proves that these inertial and gravitational masses are equal within an error of a few parts in 10 to the power 10. Okay. The rocket equation, let us take. Rocket, what do you mean by rocket? Rocket is a system of variable mass. Okay, and it works on the principle of momentum conservation and Newton's third law of motion. Now, what does it mean by system of variable mass? System of variable mass does not mean relativistic rocket. Okay, what is relativistic rocket? Suppose you have Einstein's relativistic rocket, then that rocket will travel at a speed which is comparable to the speed of light. And when that rocket will travel at a speed which is comparable to the speed of light, what will happen? There will be variation in its mass because of its velocity, because of its high velocity. But we are not considering that variable mass system over here. Over here, the system of variable mass simply implies that the actual mass change is taking place. Actual mass change is taking place. That is the meaning. Okay. So this is Newtonian rocket, not Einsteinian rocket. Okay. So rocket is a system of variable mass and it works on the principle of momentum conservation in Newton's third law of motion. So principle of momentum conservation means F external is equal to dp by dt. Okay. Force is equal to rate of external force, net external force is equal to rate of change of momentum. That is your principle of momentum conservation. And Newton's third law of motion is every action has equal and opposite reaction. That is Newton's third law of motion. Okay. So the rocket equation, let us see now. In a combustion chamber, liquid or solid fuel is burnt. You know this very well, that there is a combustion chamber in the rocket where liquid or solid fuel is actually burnt. The heat of combustion raises the pressure high enough. Okay, the heat of combustion which is there inside the combustion chamber, it raises the pressure high enough for the hot gases to be expelled from the tail of the rocket in the form of a jet with a very high exhaust velocity. So there is a rocket and inside it there is a combustion chamber, and in that combustion chamber the fuel is burnt and the exhaust gases are released from here. And when the exhaust gases are released from here, actually there is an upthrust given to the rocket, because of which it moves in the upward direction. Okay. So in a combustion chamber, liquid or solid fuel is burnt. The heat of combustion raises the pressure high enough. Okay. The heat of combustion raises the pressure high enough for the hot gases to be expelled from the tail of the rocket. And from the tail of the rocket, hot gases are expelled in the form of a jet with a very high exhaust velocity. Okay. Consequently, the rocket rushes in the forward direction, right? So the overall picture you have got, there is nothing in the previous slide except this, that there is a rocket, inside it there is a combustion chamber, gases are burnt in it, then gases are expelled with pressure in the backward direction. So as gases are expelled with pressure in the backward direction, the rocket rushes in the forward direction. That is the meaning of all these things. Okay. So deduction of the equation of motion of rocket under constant force field. Now we will deduce the equation of motion of rocket under a constant force field. Now what does it mean by constant force field? We are assuming that the rocket is moving under the Earth's gravity, and we are assuming that Earth's gravitational field is a constant force field. We are assuming like that, because we are assuming that rocket is not going much above the surface of the Earth. Okay, rocket is there at very low heights from the surface of the Earth. So we are considering a rocket of the older times. Okay, when the rocket didn't go at a very high height. Okay, it used to go at a very low height as compared to the radius of the Earth. So reduction of equation of motion of rocket under constant force field we are seeing. So at a time t, you know this very well that as the height increases from the surface of the earth, as the height of an object increases from the surface of the earth, the acceleration due to gravity changes. That is, the gravitational force field is weak at higher heights. Okay, gravitational force field is weaker at higher heights and it is stronger at lower heights. So as we move away from the surface of the earth, the gravitational force field actually decreases. Okay, but we are assuming that the rocket is such a rocket which is going at a very low height. Okay, so as it is not going at a very much higher height, so that's why we are assuming that the force field acting on the rocket is constant. So at a time t in Earth's frame, okay, at a particular time t in Earth's frame, m is equal to the mass of the rocket and v is the velocity of the rocket. Okay, now you can actually see at a time t, m is the mass of the rocket. This yellow rocket is at time t, m is the mass of the rocket and v is the velocity of the rocket in upward direction, obviously. Okay, and at a time t plus delta t, what has happened? Delta m mass has been lost by the rocket because the fuel is burnt. As the fuel is burnt, so rocket will lose certain mass. Okay, these fuel exhaust gases have come out in the form of delta m. Okay, delta m mass. So exhaust gases have come out in the form of delta m mass. So that is the mass reduction which has taken place in the rocket. Okay, so in on account of its mass reduction, the velocity of the rocket has increased as it has moved upwards from the surface of the earth at a higher height. But this height is not so high that you can actually say that the earth's gravitational field will be weakened. Such high heights are not there. Okay, the height is low, but compared to this height is high, but not very high as compared to the radius of the earth. Okay, so that is the thing. So at time t, m is equal to mass of the rocket, v is equal to velocity of the rocket in Earth's frame. This is very important. In Earth's frame means in inertial frame you are talking. Okay, because Earth is treated as inertial frame for practical purposes. So at time t in Earth's frame, m is equal to mass of rocket, v is equal to velocity of the rocket. At time t equal to t plus delta t, what will happen? Delta m mass of the ejected gas jet. Okay, delta m will be the mass of the ejected gas jet. U is equal to velocity of the gas jet. Okay, and v plus delta v will be the velocity of the rocket of mass m minus delta m. So the situation has been shown over here that this ejected gas jet has velocity u, this m minus delta m, that is the rocket which has lost its mass. Okay, so after losing its mass delta m, it has gained a velocity delta v. Okay, and the time which has elapsed is actually delta t. Okay, at t equal to t plus delta t, what happens? Delta m is equal to mass of the ejected gas jet, u is equal to velocity of the gas jet, v plus delta v velocity of the rocket of mass m minus delta m. Okay, if we treat both parts as forming one and the same system, which two parts? This rocket and its ejected gas jet. Okay, this particular rocket and its ejected gas jet, if you consider them to be these both parts as forming one and the same system, so it will be considered as an isolated system over here. Okay, although in reality this system is not isolated. Okay, in real life, but in our particular case we are considering that both these parts are forming one and the same system. Okay, and we are also ignoring the air resistance. Now you know this very well that whenever a rocket moves upwards, it has to face some air resistance. Why it has to face some air resistance? Because Earth has an atmosphere. Okay, if you launch a rocket from the moon, then that particular rocket will face no air resistance. Why a rocket launched from the moon will face no air resistance? Because moon has no atmosphere. So these equations will definitely hold in case of a rocket launching from the moon, but these equations in real life on earth will not hold because earth has an atmosphere. Okay, but we are taking the idealistic situation over here, and we are considering that both these parts, this particular part and this exhaust gas jet, both these parts are forming one and the same system. Okay, so for a finite time interval delta t, what will happen? We can actually conserve the momentum. Okay, so by the law of conservation of momentum, what do you have? We can have that F external, because this particular ejected gas jet and this particular rocket, this particular ejected gas jet and this particular rocket have been considered to be a part of the same system. Okay, so initially the rocket was there, then the rocket has taken a certain height. Okay, it has reached the delta t time has elapsed in this particular case, and delta m mass has been lost in this particular case. Then this rocket and this particular ejected gas jet, they are forming one and the same system, so we can actually conserve the momentum. So these two are inside one and the same system. Keep this thing in mind. These two are forming one in the same system, and that too an isolated system. Okay, that too an isolated system. So we can write F external is equal to Pf minus Pi. Okay, you know right. So you can write F external, that will be equal to Pf minus Pi divided by delta t. That is the rate of change of momentum is equal to external force applied. Okay. Now Pf, that is the final momentum. What is it? Final momentum is mass into velocity. The final mass is m minus delta m, and the final velocity is v plus delta v. So the final mass into the final velocity, that is your Pf. Okay, final momentum, and your Pi, that is your initial momentum. What will it be? Initial momentum will be mv. Okay, this mv, but this Pf is not complete yet. M minus delta m v plus delta v. Okay, it is the momentum of this particular part, but this particular part, as it is forming one and the same system, so you will also have to add the momentum of exhaust gases. So this is the momentum of the rocket and this is the momentum of the exhaust gases. When you add both of these together, it will be your final momentum of the system, and your initial momentum of the system is mv, and delta t time has actually elapsed. Okay, so final momentum, this much is final momentum minus initial momentum divided by delta t time which has elapsed. This will be equal to your F external. This will be your F external. Okay, so when you multiply this, what will happen? M delta v by delta t. Now let us look at over here. M delta v by delta t. Okay, M delta v by delta t. Then v delta m by delta t. Okay, so all these terms, when you open this particular bracket by multiplying mv, delta m delta v, m delta v. Okay, when you open this particular bracket, so how will you open that particular bracket? You must be knowing, right? A plus b into c plus d. What does it come out to be? It comes out to be AC plus AD plus BC plus BD. Okay, so AC plus AD plus BC plus BD. That is how you open the bracket. You have learnt it in the 7th standard. Okay, so you will open the bracket in that manner only. So, and this final bracket will be opened when you take this minus sign. Okay, so this particular bracket has been put just to show you that this PF, okay, that is the final momentum. Okay, this final momentum is over here written inside this square bracket. That's why we have put this square bracket in order to show this term, the pf corresponding to this much term, okay, and pi corresponding to this much term. In order to show that, we have put these square brackets in the outside. Otherwise there is no actual meaning of this square bracket put outside. Okay, so f external is equal to m delta v by delta t. If you simplify all these things, you will get this. Okay, now you will find that some of the things are missing over here. Which thing is missing? This particular term is missing, mv by delta t. This particular term is missing, you will find this. Okay, mv by delta t is missing. The reason why it is missing is that we are considering that the initial time is the time t equal to t is the time where the rocket was at rest. We are considering this particular rocket at time t equal to t to be at rest. So that's why this v vector will turn out to be equal to 0. So that's why this particular term comes out to be equal to 0. So all the other terms you can see over here. Okay, no, it's not like that. This mv and mv will cancel out actually. Okay, sorry, really very sorry. This mv, okay, this mv, when you open the bracket, and this mv will actually cancel out. Okay, so you can see it. If you want, I can open it for you over here. Okay, mv plus m delta v, okay, then delta m v minus delta m delta v, okay, plus delta m u minus m v. Okay, so this particular term and this particular term will cancel out, and obviously you have delta t along with you in the denominator. Now 1 2 3 4 terms, right? So you have 4 terms over here. Which are the 4 terms? This particular term, okay, this particular term is there, then this particular term is there, okay, then this particular term is there, okay, then this particular term is there. Okay, so you have got basically 4 terms. So you got the 4 terms over here. Now if delta t tends to 0, that is mass of the system, and the mass of the system is also continuously decreasing. Now what does it mean by delta t tends to 0? Delta t tends to 0 just means that a differential time has elapsed. Now a differential time has elapsed means very low amount of time has elapsed. So suppose your rocket, okay, suppose this was your rocket, and you studied the rocket at a particular time t equal to 1.01 second. Okay, so you studied the rocket at time t equal to 1.01 second. Then dt time, delta t, that is differential time, has elapsed. What does it mean? You will study the rocket at t equal to 1.01, okay, 1.01 0 0 0 0 0 0 0 0 0 0 0 0 0 1, like this. Okay, so that's the meaning of how much time has elapsed in this. How much time has elapsed in this? 1.01 0 0 0 0 0 0 0 0 0 0 1 minus 1.01. So this much time has actually elapsed in it. Okay, 0.000000000001. This much time has elapsed. Okay, so that is the meaning of delta t, time has elapsed. So this is your equal to delta t actually. Okay, So this is the thing. Now if delta t tends to 0, that is mass of the system is continuously decreasing, then what happens? Your delta term will be written as differential, that is d. Okay, so delta will turn out to be d. So limit delta t tends to 0, so delta v by delta t, it will be equal to dv by dt. Why it is positive sign over here? Why is it positive sign over here? Because the velocity of the rocket is increasing. Because as the rocket attains height, the velocity of the rocket is increasing. That's why delta v by delta t has been taken as dv by dt over here. Then limit delta t tends to 0, delta m by delta t. What will it be equal to? Minus dm by dt. It will be equal to minus dm by dt. Why it will be minus dm by dt? As mass of the rocket is decreasing, so it will be minus dm by dt. So it has lost certain mass in the form of exhaust gases, so it will be minus dm by dt. And delta v in this particular time interval, in this small time interval which you can see over here, this particular small time interval, there is virtually no change in velocity. So there is virtually no change in velocity. So you have taken the velocity to be constant for this small interval of time. So delta v is equal to your 0. Okay. So your this particular term, okay, this particular term will turn out to be then equal to 0. Okay. So you have got the f external to be m dv by dt plus v dm by dt minus u dm by dt. Okay, plus v dm by dt minus u dm by dt. Got it? Then you have actually substituted all these things. Okay, you have done nothing but you have substituted all these things which you can see over here. Okay, all these things which you can see over here. Okay, in this particular box, all these things have been substituted in this particular equation. In this particular equation. Okay, so in this particular equation you have substituted all these things, so that's why you got this particular thing. Okay, then f external, taking these two terms on the left hand side, these two terms on the left hand side, what do you get? M dv by dt equal to f external plus u minus v dm by dt. Okay, this minus will become plus, this plus will become minus on the left hand side. Okay, so you can see this thing. Then m dv by dt equal to f external plus u relative. Now this is u relative. Why this is u relative? Because u is the exhaust gases velocity with respect to earth. Okay, what is your u? This u is exhaust gases velocity with respect to earth. Now if you want to take the exhaust gases velocity with respect to this particular rocket, then what will you do? U vector minus v vector, right? With respect to rocket, u vector minus v vector, right? So u vector minus v vector, this is the exhaust gases velocity with respect to the rocket. So it has come out to be u relative, that is the relative velocity of exhaust gases with respect to rocket. Okay, so this is the equation A which you have got over here. Okay, so let's continue our discussion. Okay, so there might be some noise of the fan over here, but bear with me. Okay, so m dv by dt equal to f external plus u relative dm by dt. This is your equation A which we have got over here. Okay, now u relative is equal to u minus v. This is exhaust velocity of the rocket, right? This is your equation B, and this is known as your exhaust velocity of the rocket, as we have already learnt in the just 10-15 minutes ago. Okay, in equation A, F external is the external force acting on the system. Okay, so over here this F external is the external force acting on the system. Okay, and U relative dm by dt is known as the thrust. Okay, you must remember this thing. The U relative dm by dt is known as your thrust. Now if you check the dimensions of this particular thing, this is meter per second, this is mass, that is kg per second. Okay, so it is kg meter per second square, so units of force. Okay, and only two similar quantities can be added which have same dimension. So this is the dimension of force, so there must be, this must also have dimension of force only then both these things can be added, right? So in equation A, F external is the external force acting on the system, and U relative dm by dt is known as thrust exerted on the rocket by the ejecting gas. Okay, here the external force F external is the force of gravity on the rocket. Now this is very important point. F external, what is the external force? You will have to work against the gravity, right? The rocket system works against the gravity, so gravity will exert some. This is your isolated system, see over here, this is your isolated system. Okay, now this isolated system, on this isolated system there is only one external force, that is the force of gravity which is acting downwards. Okay, the downward acting force of gravity is the only external force which exists on this system of exhaust gases and rocket, right? So F external is the external force acting on the system. U relative dm by dt is thrust exerted on the rocket by the ejecting gas. External force is the force of gravity on the rocket, and the air resistance. Okay, the air resistance we are going to neglect. Okay, the external forces acting on the rocket are just gravity and air resistance. Other than that, there is no other force which is acting, but we are neglecting the air resistance. So now neglecting the air resistance and variation of gravity with altitude, now this rocket is going to higher altitudes. The rocket which is over here, it is going to higher altitudes, and you know this very well that when height is comparable to the altitude is comparable to the radius of the earth, in that particular case the force of gravity, that is your field, gravitational field, decreases with height. Now you have achieved certain height with the help of this rocket, but we are assuming that there is no variation of gravity with height. Okay, so we may write F external equal to weight of the rocket, because external force which acts on the rocket will be equal to the weight of the rocket. That is the only external force. So mg. Okay, mg vector, g is the acceleration due to gravity vector. Okay, so also for simplicity we assume exhaust velocity u relative is constant. Okay, so for simplicity what are we doing? For simplicity, see over here, for simplicity we assume that exhaust velocity u relative is constant. So let us assume that this velocity u relative, u minus v, this is constant. Okay, for simplicity we assume like that. Okay, so now equation A becomes, what is your equation A? This is your constant. Okay, so equation A now becomes, over here we will place mg, right, in the place of F external. So let us see, m dv by dt, so this term is as it is. Okay, m dv by dt is as it is. Now mg, so in the place of F external we have put mg, then u relative dm by dt. So the equation is as it is, but we have put mg vector in place of F external. That's it. Now this is your equation C. Here v is directed upwards and u relative and g downwards. Now you understand this, that your v is directed clearly upwards because the rocket is moving upwards, so v is directed upwards. Now this u, okay, it is, what is it? Exhaust velocity of the gases. Okay, so it is towards the ground. So suppose you consider this direction to be positive and this direction to be negative. Okay, so what will happen? Your g vector will be in the downward direction. Acceleration due to gravity will be in the downward direction because ground is over here. Ground is over here. right? Here v is directed upwards, right? V is directed upwards, U relative and G downwards. Now this U relative, why it will be downward? Because your rocket is moving upward and your U relative is exhaust velocity of the gases with respect to rocket. Now with respect to ground also the exhaust velocity is downward only, and with respect to rocket also it will be downward only. A person sitting on the rocket will feel that exhaust gases are going in the downward direction. So U relative will also be in the downward direction, right? Because of this. So U relative will also be in the downward direction because of this. V is directed upwards and U relative and G downwards. Assuming V is anti-parallel to U relative. Now let us assume that your V, what is your V? This V, okay, which is in the upward direction, and this U which is in the downward direction. These are anti-parallel to each other. So why are they anti-parallel to each other? Because we are assuming that the rocket is perpendicular to the ground. Okay, we are assuming that the rocket is making 90 degrees angle with the ground. Only then those will be anti-parallel. If the rocket is like this, suppose in the oblique position, then what will happen? If the rocket is in such a position, this is your ground and the rocket is tilted, then surely your U and V, in that case your U and V will not be anti-parallel, but we are assuming them to be anti-parallel. That means your rocket is perpendicular to the ground. Okay, you must remember. So assuming V is anti-parallel to U relative, taking magnitude of vectors in equation C. So we will put the sign convention in equation C. We have taken the sign convention when we remove the vector sign in a rectilinear motion, that is in a motion in a straight line, in a motion along the straight line. When we take upward direction as positive and downward direction as negative, okay, then what happens? Then you can remove the vector sign. You can actually remove the vector sign and write the plus and minus sign instead of vector sign, instead of vector symbol. Instead of such a symbol, if the G is downwards, then you will write minus G, okay, and your V is upwards, right? So instead of V vector you will write minus V, plus V, because upward direction is taken positive. So you can put the sign conventions now. So let us see what happens after putting the sign conventions. Okay. V is anti-parallel to U relative, taking magnitude of the vectors in equation C we have. What happens then? M dV by dt equal to minus mg minus U relative, because G and U relative were downwards, so they have been opened. The vector sign has been neglected, means removed, and minus sign has been put instead of it, because they are in the downward direction, and this V is in the upward direction. So it has been taken with a positive sign by removing the vector symbol. So this becomes negative, this becomes negative, this is positive because it is in the upward direction, these two are negative because they are in the downward direction. So your equation C becomes like this. Okay, then what will you do? This dt, okay, you will actually write the differential equation in such a manner that this dt will be written on the right hand side. Okay, so dt, writing the dt on right hand side and dividing by m on both the side. So when you divide by m on both the side, this m and this m will cancel out and one m will come over here, and this dt will go like this. Okay, so dv equal to minus g dt minus u related dm by dt. Never say that multiplying by dt on both the side. As soon as you write in the bracket over here, if in the bracket suppose you write multiplying both side by dt, suppose you write like that, then you will lose marks. Why you will lose marks? Because this is not a digit. This is not a digit. This is not a digit. This is a differential symbol. So differential symbol, it appears that you are multiplying both side by dt, and this dt will cancel out. Over here dt will come, over here dt will come, this dt and dt will cancel out. You are thinking like that in your mind, but it is not truth. The truth is very different. The truth is this differential will be equal to this differential. That is the only truth. Okay, it is not true to, it is not right to say that multiplying both sides by differential quantity dt. It is not correct to say like that. Okay, so keep this thing in mind. Never write in the bracket over here that multiplying both sides by dt. Never write like that. It is a completely wrong concept. Okay, although it appears that we are multiplying both sides by dt, then dt cancel, dt comes over here, dt over here, then dt cancel. We are thinking like that in your mind. In our mind we are thinking like that so that we can solve the problem, but reality is not like that. Okay, only reality is this differential will be equal to this differential. That is the only reality. Okay, because they are not digits. If suppose you had dv by 5, if you had dv by 5, then it is correct to say that multiplying both sides by 5, then it is correct to say. But over here we don't have number, we have differential quantity dt, so it will be wrong to say like that. Okay, so hopefully you got what I mean. So integrating from the beginning of the motion, that is t equal to 0 to v equal to 0, when there was 0 time, at time t equal to 0 the rocket was at rest. So rocket was at rest, that's why v equal to 0 at t equal to 0. So we are integrating from the beginning of the motion, and mass of the rocket m naught. Okay, initial mass of the rocket was m naught, and up to an arbitrary time t we are integrating it. Okay, so mass of the rocket at time t becomes m and velocity becomes v. So initial velocity of the rocket 0, final velocity at time t equal to v. Initial time t equal to 0 and final time t equal to t. Initial mass of the rocket m naught, final mass of the rocket m at time t. Okay, at time t mass of the rocket becomes m, and at time t equal to 0 mass of the rocket was m naught. So we integrated it. Okay, and u relative is your constant. Okay, so it will come out of the integral symbol. When you put integral sign over here, when you put the integral sign, what happens? This u relative, as it is a constant, it will come out of the integral. So integral will be applied over here only. We have assumed that u relative, that is the exhaust velocity of the gases with respect to the rocket, is constant. We have assumed like that. Okay, so u relative is equal to constant. So what did you get in the final? Finally what did you get? V equal to u relative ln m naught by m minus gt. Okay, so this is your, suppose, equation number D. Okay, so this final equation is known as your equation of motion of rocket. Okay, this final equation D is what? It is known as your equation of motion of rocket. Okay, the rocket equation. That is the rocket equation. So the rocket equation, you have, this is your what? This is the required rocket equation. So write over here that this is the required rocket equation. Okay, just write it over here, the required rocket equation. Okay, so that is how you can do the things. So we will learn about the next things in the next class. Okay.